Hey guys, what I want to do now is pause through this video series and work an example with you. So this is only going to entail London dispersion and dipole, but I think it's important to kind of break this down and make sure we're understanding it. So here's an example of a problem that I could ask you. So which of the following would you expect to have the strongest intermolecular forces? So go ahead and pause this video, work through the example, and then play the video, and you'll see how I would work through it. All right, so first things first is we need to determine what types of intermolecular forces each of these molecules have. So what I'm going to do now is I'm going to break down each molecule. So the first one's going to be carbon dioxide. So I'm going to draw the Lewis structure, determine if it's polar or nonpolar, and then decide what kind of intermolecular forces we have. So carbon dioxide. Carbon is going to bring 4 valence electrons to the party. Oxygen's going to bring 6, and I've got 2 atoms of oxygen. So it's going to be a total of 12. So 12 plus 4 is 16 valence electrons. Skeletal structure. So we got 2 oxygens and a carbon. So probably going to look something like this. Distribute to make everybody happy. So we're going to go, whoops. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I've distributed all of the electrons. Is this a Lewis structure for carbon dioxide? No. So what's wrong with this structure? Well, when I go back to see if everybody's happy, if everybody has 8 valence electrons, I look at this oxygen here and he's got 2, 4, 6, 8. So he's happy, he's good. This carbon here has 2, 4, 6, and this oxygen here has 2, 4, 6, another . So if we've distributed all of the electrons, and we don't have any more to give away, what we can explore now is double and triple bonds. So what I'm going to do here is I'm going to take away from somebody that's happy and throw it into a double bond. So I'm going to take away from this guy right here. Okay, I'm going to throw it into a double bond. There we go. So does this fix the problem? Is everybody happy? Well, this guy still has 8, so he's still good. Carbon now has 2, 4, 6, 8. He's good, he's happy, but this guy is still not happy. So I started with 1 double bond. Well, let me explore another double bond. So again, I'm going to take away from somebody that's happy, take lone pairs away from somebody that's happy and put it into a bonding pair. So I'm going to move those 2 electrons right here. So move them. Okay. Now I need to make sure everybody's happy. I need to make sure I still only have 16 electrons on the paper. So let me go ahead and do some counting. So I have 16 electrons available, and I have 2, 4, 6, 8, 10, 12, 14, 16. So I have 16 electrons on the paper. Is everybody happy? So oxygen, 2, 4, 6, 8. He's happy. Carbon, 2, 4, 6, 8. He's happy. Oxygen, 2, 4, 6, 8. He's happy. So this is the Lewis structure for carbon dioxide. Okay. Next thing I need to decide is it a polar molecule? So I'm going to isolate one of these bonds, and I'm going to determine, is there a dipole moment there? Okay. So electronegativity for oxygen is 3.5 minus electronegativity for carbon, which is 2.5. So electronegativity difference is 1.0. So yes, there is a dipole moment. Okay. So first question, is there a dipole moment? Second question, is there lone pairs on the central atom? Well, what we see here is carbon is our central atom. There are no lone pairs on that central atom. So this is actually a non-polar molecule. So, non-polar molecule, what is the intermolecular forces that this exhibits? Well, non-polar, the only thing it will exhibit is London dispersion. Okay. So I'm just going to write London dispersion to remind myself, and I'm going to move forward. Okay. Lots of skills, right? For just one teeny tiny part of this problem. It's important that we practice these. Next one is CH3Cl. So let me erase everything. Okay, and start over. So CH3Cl. Go through to do the Lewis structure. I'm going to speed this portion up a little bit because hopefully Lewis structures are pretty easy for you now. Okay. So here's our molecule. Our central atom is carbon. But one thing I notice about carbon is it's got different things attached. So it's not 4 hydrogens. It's not 4 chlorines. It's got hydrogen, 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 chlorine. So when I determine if there's a dipole moment, I'm going to have to do it for this carbon-hydrogen bond. And I'm also going to have to look at the carbon-chlorine bond. So I need to look at both of those. Okay? So let's look at carbon-hydrogen first. So the electronegativity for carbon is 2.5. Electronegativity for hydrogen is 2.1. So the difference is 0.4. Okay. I know this falls right on that limit or right on that line. If you can go ahead and instill in your brain that carbon hydrogen is a pure covalent or a non-polar bond, that is going to make your life super easy in this chapter. So carbon-hydrogen is a non-polar bond, no dipole moment, okay? But we still have to look at this carbon-chlorine. So electronegativity for carbon is 2.5 still. Electronegativity for chlorine is 3.0. So we've got 0.5. So yeah, there's a dipole moment here. Okay. The next thing that we need to look at is the shape of this molecule. And here's an example of where things get a little bit more sophisticated. So remember my cheat was, are there lone pairs on the central atom? Well, in this case, the answer to that is no. Okay, so there's no lone pairs. But hopefully when you step back and you look at this molecule, this imbalance between the hydrogen and the chlorine starts to stick off the paper. So while there's no lone pairs on the central atom, this still isn't an equal and opposite pole, right? So if these guys are pulling this way, if he's pulling this way, well, we've got this chlorine pulling against the hydrogen. That doesn't seem very fair. So this would be like Miss Mazz pulling on electrons over here, and this would be like my son David pulling on electrons over here. Who's going to win that battle? Yeah, Miss Mazz is going to win that battle, right? So even though there's no lone pairs on the central atom, the fact that they are not all the same atom attached is going to lend itself to being a polar molecule. So is this a polar molecule? Yes, it is a polar molecule because of this chlorine pulling this way. It's got one side that's a little bit heavier than all the others. Okay. So we've got a polar molecule. So what intermolecular forces are present here? Well, London dispersion is present because that's present in all of them. And with it being a polar molecule, we've also got dipole-dipole. Okay. Last molecule, and then we can finally answer this question, maybe. Let me do this the fast way. All right. Our last molecule is CH4. So we've got carbon, hydrogen, 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 hydrogen. Okay, so again, Lewis structure. Hopefully you're getting faster at these. Next step is determine, is this a polar molecule? So two things we got to look at. We got to isolate this bond right here. Carbon, hydrogen bond equals pure covalent. Or they're sharing them equally. Okay, so non-polar. So we've already got one no. And then also, are there lone pairs on the central atom? The answer here is also no, and they're all hydrogen. So everything's pulling equal and opposite. So we've actually got two no's in this case. So is this a polar molecule? Really, no, it's not a polar molecule. Okay. So non-polar molecule means London dispersion. That's the strongest one. Okay. So which of these would you expect to have the strongest intermolecular force? Well, I would expect this guy right here because he has London dispersion in addition to dipole-dipole. Okay. So let me just do some food for thought here. What if I asked you to rank these? So given that these other two are both London dispersion, which one do you think would have a stronger intermolecular force and why? So we can look at two things here. We can look at size and we can look at shape, okay? So let's look at carbon dioxide versus CH4. So carbon dioxide was a linear structure. So oxygen, carbon, oxygen. And CH4 is kind of a balled up structure like this. Okay. So the first thing I see here is I see a sphere versus a linear or a long straight molecule. So in this case, based on the shape, I would expect that carbon dioxide would have a greater intermolecular force just based on the surface area. So here's all the opportunity for interactions to take place versus, just right here would be an interaction to take place. So that's just based on the shape of it. What about size? When we think about size, what we're going to think about for size is the molecular mass. So if I add up the molecular mass for carbon dioxide, I'm going to have 12.011 plus 15.999 times 2. So the molecular mass for carbon dioxide would be, somewhere around 44 grams per mole. And then if I do the same thing for CH4, so hydrogen is 1.008, and there's 4 of them. And I'm going to add that to carbon, which is 12.011. So the molecular mass for this guy is 16.04 grams per mole. Okay. So again, based on size, the larger the molecule, the greater or the stronger that intermolecular force is going to be, right? So carbon dioxide is a bigger molecule. So again, I would say carbon dioxide would have the greater intermolecular force, and the CH4 would be less. So shape and size both give us the same picture here. Okay. So I hope you guys found this worked example helpful.